Hello everyone, today we will be discussing about the encoding techniques in data science. The presentation is prepared under the guidance of Dr. Dipti Patil.
Before we discuss specific encoding techniques, let us first understand where encoding fits in the data science pipeline. In a typical data science workflow, we begin with problem understanding, followed by data collection, data cleaning, EDA, and then data preparation. Encoding is part of this preparation stage. Now, why is encoding necessary? After cleaning the data, we examine the data types of each feature. Broadly, features are classified as numerical or categorical. Numerical features can directly participate in mathematical operations. For example, a model can compute averages, distances, correlations, or gradients using the numbers. However, consider a feature like city with values such as Delhi, Mumbai, or Chennai. If we feed these text values directly into a machine learning algorithm, the model cannot compute mathematical relationships. It cannot measure the distance between Delhi and Mumbai. It cannot multiply them, subtract them, or optimize them in a loss function. Machine learning models learn by minimizing mathematical error functions using the numerical computations. Since text values do not inherit numerical magnitude or mathematical meaning, they cannot be processed directly. Therefore, we must convert categorical variables into the numerical representation in a way that preserves their structure and meaning. This process is known as the encoding. Now, initially, one hot encoding seems like the perfect solution. It solves the problem of false ordering that we saw in the label encoding. Each category gets its own separate column. But the real problem starts when the data set becomes the realistic. Let's imagine we have a feature called city with the 5000 unique values. If we apply one hot encoding, it will create 5000 new columns. That means one feature suddenly becomes 5000 features. This leads to a problem called high dimensionality. And here's the fact, when the number of the features increases drastically, the model becomes computationally expensive and can suffer from the curse of the dimensionality. Memory usage increases and the training time as well. So, one hot encoding is safe, but it can become very efficient. To solve the drawback of the one hot encoding, the statistical encodings like target encoding, leave one out encoding, and frequency encoding came into the picture. We have seen that one hot encoding increases dimensionality for high cardinality features. So instead of representing each category uniquely, we ask a smart question. What does this category tell us about the target? Instead of identity, we focus on impact. This leads to idea of the target encoding. Target encoding, also called mean encoding, replaces each category with the average value of the target for that category. In simple terms, it answers when this category appears, how likely is the target outcome. So, this is the formula. Now, let's take a simple example. We are predicting a loan default. 1 means default, 0 means no default, and we have a feature called city. Now we calculate the mean default rate for each city. So for Delhi, its mean is 0.67. For Mumbai, it's 0. For Chennai, it's 1. Now we replace each city with its corresponding mean value. Delhi becomes 0.67, Mumbai becomes 0, Chennai becomes 1. This means 67% of customers from Delhi defaulted in the training data. So we have converted categorical identity into the statistical probability.
Data leakage happens when information from the future or test data accidentally influences the training process. In simple words, the model gets access to the information it should not logically have at the prediction time. In target encoding, leakage happens because we use the target variable itself to encode a feature. Now, let's take a proper example. Suppose we are predicting and the dataset is. Now, wrong way leakage happens here. Suppose we calculate target encoding before splitting into train and test. First, calculate mean per city using all data. So, for Delhi, for Mumbai, and for Chennai, now when we split the data, the train data is from row 1 to 4 and test data is from row 5 to 6. But notice something important here. Row 5, which is Mumbai with default value 0, and row 6, which is Chennai with default value 1. When we computed the mean, we already used their target values. So when we train the model, the encoded values already contain the information from the test data. That means the model indirectly knows something about the test set during training. That is what leakage is. And why is this dangerous? Because during real deployment, we won't know the future targets. But during training, we accidentally gave the model that information. So evaluation metrics becomes artificially high. Even more subtle leakage. Even if we don't include test data, leakage can happen inside training data. Look at the row 1, which is Delhi with default value 1. Its mean value is 0.67. That 0.67 was calculated using its own target value, that is 1. So, the row is partially encoded using its own answer. The model can memorize patterns. This causes overfitting. What happens if we ignore the leakage? The training accuracy becomes very high. Validation accuracy drops, and the model fails in production because it learned from the information it shouldn't have. See? Now let's see a real world example. Imagine a fraud detection system. If a rare merchant has only one transaction and it was fraud, target encoding gives value as 1. Model now assumes that merchant is 100% fraudulent. That is unstable and unrealistic. In real life, one transaction is not an evidence. So, data scientists asked, can we compute the mean but exclude the current row itself? And that idea leads to leave one out encoding. Core idea. Leave one out encoding calculates the mean target for a category but excludes the current observations target from the calculation. Let's take the same example. Predicting loan default. And the dataset. Step 1. Compute total per category. Step 2. Apply leave one out formula. The formula is now for row 1 with value Delhi and y equals to 1. For row 2, Delhi and y equals to 0. For row 3, Delhi and y equals to 1. So Delhi rows get 0.5, 1.0 and 0.5. Notice something interesting. Each row now has a slightly different encoding value because we removed its own contribution. Now for Mumbai and for Chennai, only one row. Count minus 1 equals to 0. Division by 0 problem. So in such cases, we replace with global name. What just happened? Target encoding gives one value per category. Leave one out gives one value per row. It is more precise and it reduces self-leakage. Why it's better? Reduces compared to simple target encoding. More robust, works well with boosting models. Now, we have seen encoding techniques that use the target variable, but sometimes we want something simpler, something safer, something that doesn't risk leakage. And that's where frequency encoding comes in. Frequency encoding replaces each category with how frequently it appears in the dataset. It does not use the target variable at all, so it is completely unsupervised. In simple words, instead of asking how does this category behave, we ask how common is this category. Let's take a simple example, the dataset. Now, let's calculate the frequency encoding. Step 1, count occurrences. Step 2, count encoding. And the step 3, frequency encoding. Divide by total rows. So for Delhi, the value is 0.33, for Mumbai 0.50, and for Chennai 0.17. What does this mean? It means Mumbai is more common in the dataset and Chennai is the rarest. So the model now knows which categories are frequent and which are the rare. But it does not know how they relate to the target. And that's the beauty of it.